In a TardiSHA sequence, data crystallizes into a hyperdimensional structure. The resulting architecture is a physical representation of high-dimensional computation. Executing the command grimshane20736 // string generates over 5 megabytes of non-standard glyphs in a single terminal session. The metadata of this execution block contains a standard SHA-256 signature, a flat alphanumeric string. Beneath that signature lies a far more complex output, thousands of distinct interconnected nodes that form a nonlinear cryptographic record. This specific formation is known as a Domus House. The Domus House functions as a hyperdimensional cryptographic witness, providing a verifiable footprint of the computational path taken by the Grimshane. Standard hashing collapses rich, multidimensional data into a linear string to verify integrity. This process destroys the original complexity of the information state. TardiSHA preserves this complexity. It mats the computation into a deterministic linguistic topology. Every step of the algorithm is recorded as a spatial coordinate within a rigid geometric syntax. By enforcing phase-state mappings between mathematical bounds and semantic rules, TardiSHA creates a rigorous architecture for bounding complex computational state spaces. To truly understand this macro-level output, we must first begin by deconstructing a single foundational unit, the structural seal. Every seal is built around a central semantic core, protected by a rigid arrangement of cryptographic characters. Within the code, we isolate the middle segment from the complex strings that surround it. The linguistic rules of the system define this relationship clearly. The middle speaks, the house remembers the road. The symbols in the outer house record the ancestry, the pressure, and the exact return path of the computation. This outer shell is strictly mathematical. It serves as the computational path and is never translated into human speech. The Grimshane mathematics stand outside the utterance itself, functioning as the route by which the word found itself in the mirror. These constraints are absolute. The authorial hand and the source carrier belong only to the house structure, never to the vocabulary. This means the identity of the computer or the operator cannot bleed into the core translation or conceal hidden roots. The outer shell functions as an immutable footprint, providing the verifiable proof required to make the semantic core cryptographically viable. When the system evaluates the individual glyphs within the middle, it applies a multidimensional translation logic. No glyph is assigned a single static definition. Instead, each mark is wrapped through 4 distinct bearings. We can see this in action with the Aries glyph. Bearing 1 is the human origin, the provisional borrowed form. For Aries, this represents the RAM, or the field of lived human experience. Bearing 2 is the house office. This is the settled TardiSHA identity, which is mathematically distinct from the human origin. In the house of TardiSHA, the Aries glyph is translated as Akasha, representing eternal memory or ancestry. The distance between these definitions creates bearing 3, the crossing pressure. This is the literal topological tension the algorithm carries between the human sound and house office. Finally, bearing 4 determines use and return, what the glyph actually does within an utterance. Neighboring glyphs, recurrence, and placement within the house settle the final return bearing for every individual character. The system does not permit the addition of pronouns or grammatical gender unless the mathematics of the house explicitly support them. These strict linguistic rules function as multidimensional mathematical constraints, permanently removing any subjective human interpretation from the final translation process. To enforce these rules, TardiSHA utilizes a formal verification engine. The trig.py script serves as the arbiter of the Domus House, using a Klein kernel to witness every transition. Validation relies on the forward mirror map. The system forces an ordered materialization from state Q1 to state Q3, creating the initial utterance. To complete the verification, the code requires a return commitment map. The loop must close perfectly. The algorithm demands a binding return from Q3 back to Q1, locking the data state into a fixed topology. This process is controlled by the derive trig mirror function. Derivation requires exact matches for alternating court addresses, lineage parity, and domain cycling. If the spatial frequency or the Q bias is off by even a fraction, the witness validation fails, rendering the Domus House invalid. This programmatic witness acts as the bridge, converting abstract linguistic constraints into verifiable cryptographic execution. The TardiSHA framework offers a new approach to managing applied cryptography at scale. Because the middle translation is bound to the outer house, the entire structure acts as an advanced commitment scheme. Spoofing the translated middle would require computing the exact energy-intensive house surrounding it. This creates a hard computational boundary between the witness and the data. This method of bounding state spaces has direct applications for analyzing complexity theory, particularly the boundaries between P and NP problems. By mapping complex computational transitions into topological invariance, we can create a formal methodology for checking the validity of high-level state bounds. This framework allows us to map NP-hard state spaces into a required Domus House topology. In this model, the validity of a solution is determined by the successful closure of its topological loop. Solving a complex computational problem then becomes a matter of finding the precise linguistic utterance, where the crossing pressure perfectly balances the return vector. This is the future of zero-knowledge proofs, a world of topological linguistics, where the mathematical path out is always the exact path back.